Good morning. Today we are going to see about the symmetrical short circuits. So what is symmetrical short circuits? Already we have discussed this kind of symmetrical short circuit faults in our previous classes in a brief. Symmetrical fault is defined as simultaneous short circuit across all the phases. So that is a three-phase fault. It is also called a three-phase fault. It is simultaneous short circuit in the three phases. Say, for example, this condition, symmetrical kind of faults, this condition might be happens in the like very less time because simultaneous short circuit in all the three phases will not occur, but sometimes it may possible that's why the frequency of the occurrence of the fault is somewhat 5%, but it is the most severe fault. If it happens means it is one of the most severe fault, that is three phases getting short circuited. Say for example, one transmission tower is there, or the distribution transmission line is there for 11 kilovolt or 33 kilovolt. So one tree is there near to that pole. So that tree is falling onto that line, and all the three phases getting damaged, and it touches the ground, and all the three phases touching each other, and it touches the ground. So like that, it is one of the most severe fault. It may happen so once in a blue moon. But even though if it happens, we need to rectify the fault, and also the time taken to rectify the fault will be somewhat more when compared to normal line to ground fault. The other two phases carries identical current except for the phase shift. So in this condition happens, the other two phases carry identical currents. Next, the reactance of the synchronous generator under the short circuit condition is a time varying quantity. And for analysis, these three reactants were defined. Already we have seen one diagram in that what is a subtransient reaction, how it happens, what is transient reaction, what is a steady state synchronous reactance. That everything we have seen in that diagram itself. But even though here the reactance of the synchronous generator. So synchronous generator, you see, majority of our power plant generators, say for example, if you take your hydro power plant, if you take your thermal power plant, majority of the your generators are synchronous generators only, synchronous generators. So sometimes under the short circuit condition, if a short circuit condition happens near to the synchronous generator, so it is a time varying quantity. For analysis, we have taken this three quantities, that is XT dash, XT double dash. First, XT double dash is nothing but subtransient reactance for first few cycles. Subtransient reactance for first few cycles. Next, XD dash is nothing but transient reactance for the next 30 cycles. Transient reactance for this next 30 cycles. And XD is nothing but a steady state synchronous reactance. So XD double dash, subtransient reactance, XD dash, transient reactance for only few cycles. So transient may occurs for only a few cycles. Okay, few cycles means some 30 seconds. So few cycles means subtransient reactance. Say for example, as I said, so one line, two lines are there. Two lines, in that one line touching other line for just a millisecond. Okay, just a millisecond or a microsecond, like that it is touching and coming back. So in that condition, subtransient reactance might be happens in that particular thing for first few cycles, only for very few cycles. Might be some 1 or 2 cycles or 4 cycles, 5 cycles. So this transient reaction, that is XT dash, will be there for 30 cycles. Like transient means some sudden induced in the some current or voltage. Say for example, lightning. So lightning also it may happen just for some few cycles. Few cycles means some 30 cycles. It may last for, see, in the particular line in a substation, they can monitor this transient. Okay. say for example, it is raining heavily. So in that time, they will be very more cautious because suppose lightning may falls on the particular line, so automatically it will trip. But even though if that is happens, so that might be any fault. Okay, that may be that may be some so due to the lightning, that may be sudden induced in the fault. The conductor conduction may it may become insulated. The conductor may become insulated sometimes. The what do you call the current carrying capacity of the conductor may lost sometimes. Okay, so that what you call the molecules inside that particular conductor may change, and sometimes due to that it may break. The conductor may break because more voltage. Say for example, one conductor may carry some 1 mega amperes. For example, 1 mega amperes that conductor may carry. So in that particular conductor, there is some 10 to the power of 6. Okay, 10 to the power of 6. It may increase up to 10 to the power of 6. So what happens is, so that much current may pass. That much current may pass. That current, that conductor can't withstand. So in that particular condition, what may happens? It may break. That conductor may break, or suddenly the tripping will be happening. But even though the conductor may break, because that much heat may generate. That much heat, even though it is raining, even though the climate is very cool, so that much heat may induce in that particular line. So the conductor, sometimes the conductor capacity will lose. That is, the conductor may become insulated because of this very high voltage. Because they say for example, you're heating that particular conductor for more temperature. More temperature. Say for example, that conductor temperature might be of some 30 degree or 40 degrees Celsius or 50 degrees Celsius. So that may goes to 500 degrees Celsius or 1000 degrees Celsius for 30 cycles, for few cycles, for some cycles. So in that condition, the current carrying capacity of the conductor may lose. So we need to replace that conductor sometimes. So say for example, when wherever that lightning may happen, from there to wherever the tripping may happen. So that say for example, some few more kilometers we need to change that conductor, like that. Some things are there. So here XD is nothing but steady state synchronous reactance. The duration of short circuit current depends on the time of the operation of the protective system. So time of the operation, as we said, like a few cycles for a time. So cycles means so it may happen for some few milliseconds, like so time of operation of the protective system. So protective system at what time, say for example, some few milliseconds, that protective system may detect that fault, and it breaks the circuit, like that. So here subtransient reactance is used for determining the interrupting capacity of the circuit breaker. Next, transient reactance XD dash is used for relay setting and coordination. Relay setting and coordination. That is called your transient stability study. Next, a short circuit represents a structural change in the network, which is equivalent to the addition of the impedance. Addition of the impedance. Short circuit represents a structural change. As I said, it may increase the size of the conductor. Increase the size of the conductor is the virtually it may increase, because that current the capacity is 0.5 mega amperes. So suddenly, due to this lightning, it may goes to some 1000 mega amperes in for a few cycles, for 30 cycles, like that. So that is structural change may happen. Structural change may happen. That much current that first of all, that conductor may not able to carry. Okay, so heavy heat in the conductor. So due to the heavy heat, sometimes break in the conductor, break and fall to the ground. So like that, many things, as I said, the conductor may damage. Sometimes the conductor may burn for certain kilometers. So we'll tell like kilometers. So whenever you're purchasing the transmission line, so you need to purchase in kilometers because or miles. In north eastern countries, they may purchase in miles. In the southern countries, they may purchase in kilometers. They may purchase in kilometers. So 500 kilometers, 300 kilometers, like that, 100 kilometers, like that. Depend on the capacity, they may purchase the conductors in the kilometers or miles. In this much miles we need to purchase, like that. They may purchase. So as I said, structural change. So it is nothing but equivalent to addition of impedance. So addition of some impedances in the line. In case of symmetrical short, with the three equal impedance at the location of the fault. So three lines it is happening means three equal impedance at that particular fault. Then the post-fault voltage and the currents in the network are obtained by superimposing these changes on the pre-fault. So how we are calculating is we are assuming that post-fault voltage and current in the network are obtained by superimposing these changes on pre-fault voltages and the currents. So that also we are doing. Next, Thevenin's theorem and its application. So how to define this Thevenin's theorem now? In any linear bilateral network, so all the say for example, how many voltage sources are there? So that might be replaced by one voltage source, that is Thevenin voltage, and also the resistance. Say for example, this much resistance, many resistance are there, or many impedance are there. That is replaced by the one resistance or R Thevenin. Okay, the Thevenin resistance or impedance Z Thevenin. So that is replaced by that is we are connecting that voltage source that is in series with the impedance or series with the resistance. So that is called your Thevenin's theorem. That is the changes that takes place in the network voltage and currents due to the addition of an impedance between the two network nodes are identical with those voltage and current that would be caused by an EMF placed in the series with the impedance and having a magnitude and polarity equal to the pre-fault voltage that existed between the nodes, and all other sources are being zero. So all other sources are being zero. So this all the voltage source that is replaced with a one equivalent voltage source, that is E Thevenin, and all your resistance or impedance that is replaced with a one equivalent impedance, that is Z Thevenin. Okay, so all other sources are become zero. The Thevenin equivalent circuit that is shown in the figure. So this is the what are the applications? So the main application of Thevenin's theorem is the fault current can be evaluated easily. Next, the bus voltage and line currents during the fault can be determined. Post-fault voltage and current can be obtained by using the pre-fault voltage and current. So post-fault means after the fault, whatever is happening, that a voltage and current can be obtained by the pre-fault voltage and the current. Next, the bus voltage and line current during the fault can be determined. So at that particular fault, the bus voltage and line currents. So that is during that fault also can be determined easily. Next thing is that short circuit analysis of the two bus system. So here we are analyzing a short circuit for a two bus system, because in power system, practical power system, you see, there will be not only two bus system, there will be a many buses are there. Say for example, in a particular substation, if you select that, there might be some three bus system or four bus system. It depends on the capacity of the your that particular substation. Say, for example, for consideration, in this system, we have taken only two bus system. That is, we are having two generators that is connected by a transmission line and as well as your transformer. So that is this and a two-bus system as shown in the figure. Next, in power system, loads are specified and load currents are unknown. So loads, in the substation, they know what is the loads and the load currents. Load currents, how much that load may consume, that we can't. But approximate load we know. But how much load currents are consumed, that is depends on the climatic condition and what is the mood of the particular consumer. Say, for example, in hot summer, it is raining. So that time the load will be less because the climate will itself will be very cool. So the current consumption of that current will be less. So say, for example, it depends. Say, for example, it is very, very hot. That condition, the load currents may be increased like anything, because every ceiling fan will be on, so every ACs will be on. So like that, it may depends on the mood of the consumers, or the climatic condition of that particular area that which your substation is being located. Next, the effect of load currents is in the fault analysis are to express the loads by constant impedance evaluated at the pre-fault bus voltage. So what we are doing is the effects of the load currents in the fault analysis. So how we are expressing this load currents in the fault in the sense that is load by constant impedance. So we are giving the constant impedance that evaluated at the pre-fault bus voltages. The pre-fault bus voltages are obtained from the results of the power flow solution. So how to identify this pre-fault bus voltages in sense we are obtained from the results of the power flow solution. So power flow solution, as we seen before, if you go back to my previous classes, so there are some power flow solutions, like we solved the power flow solution by using the Gauss-Seidel method, Newton-Raphson method. So this pre-fault bus voltages are obtained by the power flow solution. The loads are expressed by the constant admittance using the pre-fault bus voltages. So we are expressing the loads by using the pre-fault bus voltage with the constant admittance or impedance. It depends on in what perspective we have taken that fault analysis. Sometimes we mention the constant admittance, sometimes we mention the impedance like that. Next, replace reactance of the synchronous machine by subtransient or transient values. So we need to replace the reactance of that particular synchronous machine, that is synchronous generator connected at the particular bus, by using the subtransient or transient values. Next, first we need to draw the reactance diagram for that short circuit. Wherever the short circuit happens, we need to draw the reactance diagram. Next, we need to draw the Thevenin's equivalent that is weaved from the fault bus. First, you need to draw the reactance diagram. We'll see in detail how this reactance diagram is drawn. Also, I have explained how to draw this reactance diagram in our previous classes. So that class also I will give in the description and comment section, so that you can go back to my previous classes also, so that this thing will be very easy for you. Next, we need to draw the Thevenin's equivalent viewed from the fault bus. So as we discussed previously, so all the voltage sources are replaced by the single equivalent voltage source, that is Thevenin's voltage source, and as well as the Thevenin's impedance. All the impedance are replaced by the equivalent Thevenin's impedance, and also we need to identify the fault, where the fault happens. So definitely, if you replace all the voltage to as a one source, and also the Thevenin's impedance to a one source that is connected in the series with the voltage, Thevenin's voltage. And definitely, say for example, here the fault occurs means, so this is the fault current IF, and also fault impedance as ZF. So that is the this Thevenin's equivalent circuit. Next, fault current. How to calculate this fault current is nothing but Z Thevenin divided by this Thevenin impedance and as well as the fault impedance. This already you know. Okay, I is equal to V by Z. V by Z. So V is nothing but Thevenin is equivalent circuit divided by total impedance. Total impedance is this Thevenin's equivalent impedance and as well as the fault impedance. Next, determine the current contributed by the this two generators. So we need to determine the current contributed by this two generators. That is, say for example, this is the bus number 1. This is the bus number 2. The voltage at the bus number 1 is E1, and we need to mention this positive and negative terminals also here. So here also E2, this source generated two sources E2, and we are mentioning the positive and negative terminals here. And the current generated from the second generator is Ig2, and the current generated from the first generator is Ig1, and having the impedance of Z1, that is first generator having the impedance of Z1, and the second generator having the impedance of Z2, and here this bus 2, here we are having some constant, this is the fault current, no fault current, we are having a 1 at the angle of 0. That is why we are taking the 1 at the angle of 0 is it is the pre-fault voltage we need to consider as 1, as we mentioned earlier. So 1 at the angle of 0. But here due to the fault, the terminals, okay, the polarity at this terminals are changing. That is here minus, here plus, and the fault impedance as ZF. So this is the circuit for finding the current contribution by the generators. So here, what is the current at the particular generator number 1? That is Ig1 is equal to, this is by current division rule. Current division rule already you know. So that is the Ig1 is equal to this fault current. So here the fault current IF, they forgot to mention here IF. So IF into, so the current division rule, so you need to take the impedance from the second node. So say for example, this you take as first node and this you take as second node. So you need to take the impedance from the second node, that is Z2, okay, divided by total impedance, the Z1 plus Z2. That is the current division rule. So this Ig1 is equal to IF into Z2 divided by Z1 plus Z2. Next, Ig2 is equal to this fault current into the same fault current into the impedance in the like a previous node. That is, if you are taking the current in this particular node, you need to take the impedance from the like a nearby node. That is, a nearby node is this one only. So you need to take Z1 here. So Ig2 is equal to IF into Z1 divided by total impedance Z1 plus Z2. Next, determining the post fault bus voltage. Post fault bus voltage. How to determine the post fault bus voltages after the fault? So what is the bus voltage? That is V1 F is equal to V1 naught. So V1 naught is nothing but pre-fault voltage. Pre-fault voltage is what? That is 1 at angle of 0 or 1 plus J0, whatever is correct. Next, plus del V. That is change in the voltage. This change in the voltage, already we have seen this concept in our Newton-Raphson and Gauss-Seidel method itself. Change in how to calculate the change in the voltage. So pre-fault voltage, that is V naught plus here how to calculate this change in the voltage is in the sense that is Z12. So here Z12, because it is happening here, change in the voltage is happening at the fault bus itself. So Z12 into Ig1. So into Ig1. So why minus? Because this terminal fault is happening in the opposite terminal. So we are taking this minus. So minus Z12 into Ig1. Next, V2F. So voltage at the second fault voltage at the second bus. V2F is equal to V2 naught, that is pre-fault voltage, plus del V. So del V is nothing but your change in the voltage. Del V is nothing but change in the voltage. So V2 naught plus ZF into IF minus 1 at the angle of 0. So here we mentioned 1 at the angle of 0. So ZF into IF is nothing but that impedance at the fault impedance, and as well as the current at the fault minus 1 at the angle of 0. Next, how to determine this post-fault line flows? Post-fault line flows is in the sense Ij is equal to Bi minus Bj divided by Zij series. So Bi and Bj are the bus voltages. Bi and Bj are the bus voltages. That is the particular part I and J. Next, Zij series equal to series impedance between the buses I and J. So VA is nothing but voltage at the bus I, and VJ is nothing but voltage at the bus J. That is the 2 point voltages at the 2 point. That is ith bus and jth bus. So that difference divided by the Zij. That is nothing but series impedance between the bus I and J. So this is how we need to determine the post fault. Post fault. So these are the steps. Next, we are calculating the short circuit capacity. Short circuit capacity, that is SCC, or fault level, or fault MVA. Okay, fault MVA. Short circuit capacity or short circuit MVA or fault level. So these are the other names at the particular bus. So, fault, you can say like a fault level, you can say like fault MVA, or you can say like short circuit capacity. So everything is same. So short circuit capacity or short circuit MVA or fault level at the particular bus is defined as product of magnitudes of the pre-fault bus voltage and the post-fault voltage. That is nothing but product of the magnitude of the pre-fault bus voltage and the post-fault current. It is used to determining the dimension of the bus bar and interrupting capacity of the circuit breaker. So dimension of the bus bar we are determining, and also interrupting capacity of the circuit breaker. So at what current that particular circuit breaker has to interrupt. So that also we are calculating. So coming to the Thevenin equivalent circuit, as we see before, the same circuit here, the Thevenin C Thevenin. So polarity also positive and negative terminal. So Z Thevenin. So all the impedances we are converting into one impedance, that is Z Thevenin, and the impedance fault impedance. Okay, fault impedance. So that we are taking as 0 here, and the fault current IF. So this is the Thevenin equivalent circuit for a volted or a solid fault. Solid fault in the some predetermined fault. So this fault is happened like that. So that is called the solid fault and volted fault. That definition also already we have seen before. So that description also, that video also I will give in the description and in the comment section. So here the fault current. How to calculate this fault current in the sense Z Thevenin E Thevenin divided by Z Thevenin. So that is I is equal to V by Z. So next, how to calculate the fault current with the admittance, with the reactance, in the sense same. IF is equal to E Thevenin divided by Z Thevenin, that is in the per unit. So all in the per unit. So Z Thevenin is nothing but pre-fault voltage. Pre-fault voltage in sense of what is the before fault voltage that you are calculating. Next, base current is equal to MVA base divided by √3 into KVB. Okay, so base current is equal to MVA divided by √3 into KVB into 10 to the power of 3. So this also already we have seen the previous classes. So that also I will give in the comment section. So if you don't know how to calculate this base current, that you go back to my previous videos and you just clarify that. Next, fault in the kilo amperes. Fault in the kilo amperes. So mostly it is in kilo amperes. some high voltage transmission line that is in mega amperes, like 400 kilovolts line, next 750 kilovolts line, then the 1000 kilovolts line, that are all in mega amperes. So normally for distribution system or like that in a substation, and they may calculate in kilo amperes. So generally we here we are taking the like a base current as kilo amperes. So so we are also taken in the same scale, kilo amperes. So sometimes if you want to change, you can change, but the base values you need to change. Okay, that is per unit value. Accordingly, you need to change. So fault current in kilo amperes is nothing but IF, that is fault current in per unit into this base current, into this base current. That also we need to take. Or otherwise, in other terms, fault current is equal to the fault current in kilo amperes divided by this base current. That also correct. Okay, so IF is equal to E Thevenin divided by X Thevenin into this base current. The base current already you know. Just to substitute in this equation, you may just the same thing. MVA base into 10 to the power of 3 divided by root 3 into kV base. Okay, so next is short circuit capacity. Short circuit capacity SCC is equal to Z Thevenin into IF. Z Thevenin into IF into fault current. So Z Thevenin as it is. So fault current already we have calculated here. Just to substitute in this equation. So Z Thevenin divided by X Thevenin, that is nothing but equal to E Thevenin the whole square divided by X Thevenin in per unit. Okay, per unit. So the in per unit. So into MVA. So this MVA also here. So this in into this MVA. So next pre-fault voltage. As I said, pre-fault voltage, what pre-fault voltage is nothing but 1 at the angle of 0 degree. That we have seen before. What is pre-fault voltage? Next, SCC, short circuit capacity, is nothing but 1 divided by X Thevenin per unit into this MVA. So you need to multiply this MVA base. Okay, so that is in MVA. So short circuit capacity is in MVA. So here you need to, so here it is in per unit. So you need to convert into MVA base. So just you need to multiply by MVA base. So short circuit capacity is equal to 1 divided by X Thevenin into MVA base. So that is in MVA. So where MVA B is nothing but a base MVA. So this the SCC have a tendency to grow as new generator is added. So short circuit capacity, why we are calculating is say for example some new generator is added. So you can easily calculate the you can easily do this calculation. So that is why we are going for this short circuit capacity and additional lines also built. Short circuit capacity is reduced by introducing artificial series reactor. Short circuit capacity is reduced by introducing artificial series reactors. Okay, so if you want to reduce, you need to add the series reactors in the line. So that also possible. And this mainly we are calculating why, because if new generator is added and something new lines also built. Okay, new lines also built. This short circuit capacity plays a major role whenever we are adding. So that's calculation part plays a major role whenever we are adding new generators and as well as the additional lines in the particular transmission lines.